Okay, great. I'm going to talk really about kind of two different things that are connected in the middle. One is Uber's work on self-driving cars. Another is what I feel is an increasingly important area in machine learning. And along the way, I'm going to connect the two. So here's my plan. I'll start with some of the history of vehicle autonomy, and then I'll get over to the machine learning side, and then I'll come back and we'll finish up more on the future end. I think it's kind of fun just to look at sort of how far we've come in the amount of time we've been at this. Here are some vehicles from CMU. So in the 80s, this was NavLab, and of course the people have brought this up before. That maybe the defining feature of this is it was a giant van because it had to be. We needed that much space and power just to get enough computing in for this thing to do anything. I think we spoke to that before about how some of the changes we're seeing are just because the computing finally arrived, and self-driving cars are certainly one of those. You might say that the NavLab project in some ways had a culmination in doing the No Hands Across America drive. It was very exciting. This was in '95. It's hard to believe. This is now over 20 years ago that this happened. It drove from Pittsburgh to LA over 98% autonomously with long stretches with no human intervention. And of course, the other fun thing about this is that the underlying technology here was from the previous incarnation of deep learning. So deep learning has gone through a whole sort of summer, winter, spring, back again in the time since all of this happened. And of course, this vehicle, from an AI sense, it was using learning, but it really had no idea what it was doing, right? It was just looking at a lane in front of it, and it sort of knew the pattern of the lane and was trying to stay in the middle of it, but had no idea where it was going. Following that, there was more off-road work that was done, and so here's some stuff from the 2000s. And what happens here is that this vehicle at least knows where it is. It knows what its location is and knows where it's trying to get to. But it's other than that, other than just these location waypoints, it doesn't know anything about the environment. So it's just looking out there, it sees a bunch of objects, doesn't know one type from another or what it's doing, but just sees obstacles and plots paths around them. But nonetheless, was able to get some pretty good performance in pretty challenging environments. And of course, the one that everyone's familiar with is the DARPA Urban Challenge. So here there was fully autonomous driving in an urban environment. And the big changes here are now there are good maps. And what maps means in this case is not like the kind of Google map you use to see where you are when you're driving around. These are sort of high fidelity 3D maps of everything in the world. And what this does is it allows the vehicle to figure out precisely where it is compared to an already known environment. And it also allows it to pick out the other moving obstacles in the scene. Those are the things that are not in its map. And it's able to actually reason about where they're going and what they might be doing next. And of course, the cool thing about this, CMU wins. Always happy about that. But I think the real milestone here was the point where Google said, wow, okay, something seems to be happening here. We're ready to get serious about this. And this is really the point in time that the Google car project started and did it using much the framework that was developed for the DARPA Urban Challenge. Of course, CMU also saw the potential of this. And so following that, they partnered with Caterpillar to start working on autonomous trucks. And again, using a Velodyne LiDAR and radar system. And it turns out this was one of the early commercial systems that was autonomous commercial systems that was available. And here again, the main driver of this was safety and efficiency. It wasn't about much of the work in robotics. People talk about the cost of the human laborer relative to everything going on in this mine. The salary cost of the driver is not a big component. The real issue here is safety and efficiency. This truck's very expensive, and when it makes mistakes, they're always expensive ones. Okay, so scrolling all the way up to the current. So in 2015, Uber decided that it's in the transportation business, and this autonomous vehicle thing is happening. And so they opened a lab in Pittsburgh to start working on self-driving cars, and they did it with many of the people that were involved in the previous projects that I just showed you. So what I'd like to do, just thinking about that, what has Uber taken on here? I'm going to show what in any other context would be a very boring video. But to me, it's terrifying, because it's terrifying to watch this thing and think you're the person that's going to have to write the code to do this. And if you look at this, it's absolute chaos. There's people going all over the place, all directions, cars coming at you, across from you, changing directions. There are these street cars that aren't too common, but those matter. You've got to watch out for them a lot. But those lines they're connected to above you don't matter. You should try to ignore them. There are stop signs that do matter. There's billboards that say the word stop on them. You should ignore them. There's different lights where it matters what color that light is, whether it's green, yellow, or red. There are other random flashing lights that are just distractors for you. You've got to make sense out of all of this chaos and never do the wrong thing. I find this absolutely terrifying, and yet that's what's been taken on here. And so I think the result of this is, and of course Uber's not the only one doing this, the automotive market is changing a lot. And so, there's the sort of the obvious things that are changing is that on board the vehicle, we're going to have a lot more data, a lot more bandwidth, lower latencies, a lot more computing power. And even the product specs are changing. This is the one that I think is kind of fun. When you're driving the car, it's got to look good. I'm not going to drive some crappy car around. But when you're not driving, you don't care. You just want to be safe and efficient, right? What the car looks like is really not your top concern. So it's really changing the way things are designed a lot. And of course, what's relevant to all of us here is that the cars are becoming one of the most complex systems that our software will have to operate. And what that means is they are not happening without machine learning. It can't be done. It's too complex. So machine learning is pervasive throughout self-driving cars. And rather than attempt to explain all the places that we have machine learning in the self-driving car, I'm actually going to talk about one of a little bit more personal interest to me that I think is becoming increasingly important, and that's active learning and active optimization to improve the performance of cars. And so with that, I'm going to switch over to that topic. Okay, so what do I mean by active optimization? So in this case, what I'm referring to is you can assume there's some function here that's an unknown but expensive black box function. And so what you're interested in is you would like to find the maximum of this function, but you need to do it with as few experiments as possible, because the only query you can make to this is you can name value of x, and you'll get a possibly noisy response f of x from it, and every one of those is going to cost you a substantial amount of money. So you would like to find this as efficiently as possible. This goes under lots of names. The statisticians here would think of this as design of experiments. Even in the machine learning community, people tend to call this Bayesian optimization. It's very connected to bandit algorithms, and there are other similar names for this type of problem. So why do I care about this type of problem, and why do machine learning people care about this type of problem? One is it can be used to do the tuning of hyperparameters for supervised learning algorithms such as deep networks. It's actually expensive to do the training and evaluation, so you would like to search that hyperparameter space efficiently. Of course, with cars, anywhere where you've got to do an experiment on a real physical system, the experiments will be expensive, and you want to be as efficient as possible about that. Of course, increasingly, there are many tests that can be done in simulation, but even the simulations themselves are expensive. So even though you don't need to run a real experiment, you still can't run every experiment you would like to, and so you need to allocate that computation, that simulation computation, as efficiently as you can. So these are all areas where we would like to use active optimization. And so what's the framework? What we're going to do is we're going to model this unknown function as a Gaussian process. It doesn't necessarily have to be a Gaussian process, but it has some nice properties if you use one. And so we'll do that, and then the relevant thing of a Gaussian process, don't read all this stuff on here. The relevant properties of this are just that you get a nonlinear function approximation with good posterior distribution, so you get confidence intervals on your function, and you can do the inference in a nice closed form. That's what's relevant for it. So how does that look? We have some unknown function. We've taken some data points. We're going to model it as a sample from a Gaussian process. From that, we can obtain a posterior on what we believe that function to be. And from that posterior, we're going to define some acquisition function. And what that acquisition function is going to do is tell us where we should choose the next experiment. And so in this case, what I'm going to look at is just the upper confidence bound acquisition function. So what that means is you'll look at this posterior on the top and imagine the upper confidence bound there. And so what you'll do is then maximize that acquisition function, and wherever that maximum is, you're going to choose your next experiment. And you can understand this very intuitively, that a place where that's high is some combination of places where you already believe the function will be high, which is what you want, and you have some amount of uncertainty about what the function is, so you'll learn something by running the experiment there. That's the intuitive motivation there. There's lots of other acquisition functions. In the interest of time, I'm not going to talk about them, but the concept is the same. You want to focus on where things are likely to go well and where you're going to learn information by running an experiment there. So what does the whole algorithm look like? You just go through these steps here. You look at the experiments you've already run. You create your Gaussian process from it. You construct the acquisition function from the Gaussian process. You then search the acquisition function to find the highest value of it, and then you run the experiment at that point. And then you add the data point back and you repeat the whole process. And so that's what that algorithm looks like. Just to see it in cartoon form, so here's our unknown function, and the gray there is our confidence bounds for that function. And what we're going to do, so at the beginning, okay, the acquisition function's flat, so maybe we just take something in the middle. Having done that, okay, now we're more certain about the function there. That makes the acquisition function look like this. So now we're going to choose the point on the far left. Then we'll get this update to our estimate of the function. This new acquisition function, now we choose the point on the far right. And as we continue this, by the time we get to the end, sort of the right thing has happened. So if you look at the top here, what's happened is you've explored the whole function, but most of the experiments have been done near the highest parts of the function where you're really trying to hone in on the optimal for that. So that's the concept. It's fun to look at cartoons and try to understand how an algorithm works, but the question we have now is, okay, that's nice, but can we run this on real systems? Can real autonomous systems learn with this kind of method? And so what I'm going to show you is a robot we have back at CMU, a snake robot. So it's about this long. It's got 16 joints. Does all the things snakes do. It can do sidewinding. It can swim. It can climb up trees. It can hang on branches. It does all the things snakes do. But it's notoriously hard to model and to figure out any sort of controller for it because all the dynamics and kinematics have severe nonlinearities in them. And so what we'd like to do is just have this snake learn how to move around. And what I'm going to do is, in the interest of time, I'm going to skip a couple of these and just go to maybe the last one, which is the most fun. So this is a snake using that active optimization algorithm that I showed you. And what it's trying to do is learn how to get over this obstacle here. So every one of these thrashings is the snake attempting one point that was chosen from its acquisition function. And after it does the attempt, it gets some feedback on whether it got over that obstacle or not. And so what you can see here is very early on it's struggling a lot, but we made the problem easier so it would have some successes. And then what we're going to do is sort of ramp up the difficulty of this as it's learning here. And what I'm going to try to do is that's a bummer. I wanted to scroll to the end, but apparently I'm not going to be successful scrolling to the end. Okay, we'll wait just a minute for it to get one more block on there so you guys get a better idea of how it's doing. This one's not too bad. Okay. Yes. Haha, that's a great question. 3. You're already prompting me for what's on the next slide, which is good. So I'll cut this short, but this gives you, it actually can do even higher than this. But you get the idea here that by the end, it has figured out how to get over this obstacle by using that active optimization algorithm. And it's able to do one higher than that too, which is cool, but I'm just going to move on. Since I already got a question for the relevant feature here, everybody likes to watch that snake video. That's fun, and it's clearly learned something, so guess we're done. Active optimization works. The issue is that the procedure I described there, it's exponential in the dimension of the space you're trying to optimize there. And so what happens in practice is that and I skipped this. We went to a lot of effort to find a low-dimensional representation of those choreographed moves so that the active optimization algorithm could search it. But that's not what we want to do. What we want to do is have it optimize the real full problem with lots of parameters. And so we put a lot of work into that, and I'm going to show you just a little bit of it. And so, right, the challenge here is really these things you can only use in sort of 6-ish dimensions. And so what we're going to do, I'm going to skip some of this prior work. There's a lot of work in take a high-dimensional space, do some kind of low-dimensional projection of it, and then operate in that low-dimensional space, which is another version of what we did with the snake anyway. But what we'd really like to do is operate in the high-dimensional space directly. And so what we did here is we implemented an additive model. So if you can sift through all the garbage on this slide and think of those 10 variables there as a 10-dimensional space, and the coloring of them as groupings of them. What we're going to do is assume that we have an additive model, and what it really is the sum of 3 components, the sum of 3 three-dimensional functions. So one component is variables 1, 3, and 9, another is 2, 4, and 8, another is 5, 6, and 10. And so what's going to happen is now that we've decomposed this function, and we're going to operate in that decomposed space, and it will only be exponential in the size of these components in the small d. So how does that look? So if we were going to make a picture of a really low-dimensional example, here's a 2D one where we've decomposed it into 2 one-dimensional components, and so you can see them on the side. And what that means you can do is I skipped all the slide with the GP math, but it's still a Gaussian process, and what you can do is you can optimize the acquisition function for each component independently, and then take the max of each of those to choose your point, and then you repeat from there. And so it turns out this allows you to do very high dimensional functions still in a way that's tractable. I'm going to have to skip the examples, but what happens is we've done some things with scientific model function fitting and optimizing classifiers where we've done things up to 20 or even 40 variables and still optimize them with a modest number, a few hundred experiments. And there are corresponding proofs that show these become exponential in the small d rather than the large d. There are still many things left to do. How do you choose the decomposition, the size of the components? How do you do this non-axis aligned? That turns out to be a hard problem. That was published in AI Stats last year. And another thing that we're very excited about is multi-fidelity optimization, where run cheap surrogates to your real experiment. And sometimes you can even continuously vary how expensive they are and how you control that decision of which experiment to run and how much to invest in that experiment. It happens commonly in cross-validation when you look at the size of the sets you use. It happens in simulation when you can vary the fidelity of the simulation experiments. That was published last year in NIPS. I'm going to scroll past all of that, sorry, but those things are published, so you guys can have a look at those. And I want to make sure I come back on my promise to talk about sort of where we are with self-driving cars and where things are going. So September 2016, Uber launched its self-driving car service in Pittsburgh. So here are all the cars getting ready to go out. And what I'm going to do is, unfortunately, this video is sort of low content. It's basically a sort of a flashy marketing video, but it'll show you this, and then I can talk while we're at it. So in Pittsburgh now, when you request an Uber X, if you've signed up to be part of this program, you can, if there's a self-driving car that's closest to you, you'll get the self-driving car will come and pick you up. And so you can see here that the cars have a safety driver in them ready to take over. But the cars do drive around autonomously in an urban environment. This is all in Pittsburgh here. And so it's sort of very exciting progress for us to have these things to a level where you can take the rides in them. As I alluded to earlier, this car wouldn't be doing what it does without machine learning extensively through it. The active optimization at this point has mostly been offline, but I believe online will be coming as well. You can see here the display you get when you're riding in the car. So it shows you the LiDAR scans and everything the car sees. So you actually know what it sees while it's making its decision, which is a lot of fun here. What I want to do, though, is talk a little bit just about the future. Obviously, self-driving cars are going to change a lot of things. One will be car purchases. Does it make sense to own a car anymore? I think that's the big question everybody's concerned about, because it'll be right now, if you do the economics for selling your car and taking Uber everywhere, it's not quite there, except for a few rare places like the middle of New York City. But once the cars are self-driving and we're not paying the driver the 80% that the driver gets, that will cross the line. It'll be, for a lot of people, it won't make sense to own a car anymore, which is fascinating. It'll also have a big impact on the landscape of cities. That we won't need all this parking infrastructure. We'll even be asking questions. A lot of public transit schemes are done because they're, in some sense, the right thing to do. Public transit is good for your city. But from a financial point of view, they're not very efficient. And so this will cause questions of what could cities do with those resources instead when more efficient alternatives are there. This is, we're working not only on transporting people, but also things. You can, if you go on the internet, you'll see this picture of one of our trucks delivering beer across Colorado. It's lots of fun. As I mentioned already, machine learning is ubiquitous in these vehicles. It's just not possible to do this without machine learning. Sorry, I'm going a little fast because I want to get to the end. It's fun to speculate sort of further in the future. At some point, cars will be a lot safer than humans, which will also mean they can drive much more efficiently and, in fact, drive more aggressively than humans do and still be safer because of the time savings. And so it's going to free up a lot of time, money, and space for other purposes. And we can always ask the question, people always ask me, at what age of my kids will they not ever have to get a driver's license? I think it's an interesting question. So my summary, coming back to the active optimization, there's a lot left to be done in terms of scaling. And even in answering some of the hard questions that, okay, we've been optimizing this thing, but when is the system good enough to deploy? And how do we answer that sort of safety question? Is it good enough that I can put a person in it yet? And I have another question that I think is just fun. people get really worried about what happens when you embed learning into engineered systems, and has it become an unmanageable system? I would argue that engineered systems today are already unmanageable. This concept that, oh, somebody had a learned model and they changed the training data and it messed up my system. Anybody who's worked on a large engineered system knows that already happens anyway. Someone changes the design to their sub-piece and you don't realize the impact it has on yours. And so what's really happening is not that we're changing the complexity, it's just we're forced to write it down in an algorithm. How are we going to deal with it? Rather than figuring it out over the water cooler. So with that, I'll stop.